Okay. So thank you very much for the invitation, and I would love to be there in person. I'm planning to at some point in the future if the Canadian authorities allow it. And yeah, that's it. So yeah, the title of the talk is Compressible Types in NIP. This is oh shit. This is joint work with Martin Bass and Pierre Simon. Um, So the contents of the talk is as follows. First, I'll try, I don't know how much I'll get, but I'll try as much as I can. So first, I'm going to talk about local theory. So local theory means that I'm going to assume one formula is an IP, and I'll be working with local types. And then I'll talk about K-compressible types, uniform honest definitions, and hypes and pseudofinite types. So that's the local part. Then I'll go to the global theory, where I'm assuming the whole theory is an IP, and I'm working with complete types. Although I can also work with complete types without assuming the whole theory is an IP, but never mind. So then I'm going to talk about compressible types and compressible models. Okay. So I'm going to start very fast to talk about the stability. Just remind everybody what a stable formula is. I guess everybody knows. So remember that the formula is stable if it doesn't have the order property, which means you cannot find, you can see my mouse, my cursor. So you cannot find AIBJ such that phi of AIBJ holds if and only if I is less than J. And a theory is stable if every formula is stable. So examples, many examples, algebraically closed fields, equivalence relations, free groups, abelian groups and modules. And I'm continuing in stability. I'm reminding what is a definable type. Also, Martin Hills reminded it in his talk. So A is now a set of Y tuples. A phi type over A is definable if the set of instances appearing in P is definable over A by some formula psi. So there is some formula psi such that this set is an instance of psi over A. So the fact is that if phi is stable, then every phi type is definable and even uniformly, meaning the formula psi here does not depend on A, at least when A is at least 2. Okay, now I'm reminding what is a VC dimension. So X is a set and you look at a family of subsets, then we say that the set is shattered by F if for every set S in A, there is some F in F whose intersection with A is exactly S. And F as VC is a VC class, F is a VC class, if there is some N such that no subset of size, no subset of X of size N is shattered. And the VC dimension is the smallest integer N such that no subset of X of size N plus 1 is shattered by F. And then a theory is NIP if every formula is a VC class if the instances of every formula is a VC class, namely if you look at this set, okay, then this is a VC class when M is any model. And T is an IP if the formula is an IP, as I said, and a formula is an IP if this happens. So examples again, linear orders, trees, real closed fields, periodics, ACVF. So this part I'm going very fast, but I'm going to slow down now. Okay. So UDTFS. So a formula has UDTFS, which stands for uniform definability of types over finite sets, if there is some formula psi, so this formula psi depends only on phi, such that whenever A is some subset of size at least 2, any type in phi op, so phi op is just phi with the reversed variables, okay, so phi of xy, so this is a type in Y, okay? So any type P in over A is definable by an instance of psi, okay? Note that if phi has UDTFS, as witnessed by this psi, then the number of phi op types over A is bounded by A to the Z plus 2, because essentially because I need to choose the parameters to define it. Okay, so phi has to be an IP, because there's if phi has IP, then the number of types would be exponential in A, and here we see that it is polynomial in A. Okay, so here's a question of Laskowski whether NIP or NIP is equivalent to UDTFS. So Sauer-Shelach says that if phi is NIP, there is a polynomial bound on the number of types. So the question is, does it have to come from a definition? Okay. Okay. So historically, UDTFS was proved in the following cases. So first by Laskowski and Johnson in 2010 in weakly or minimal theories. Then by Gingona in 2012 for DP minimal theories. Then the breakthrough was by Chernikov and Simon in 2015 for NIP theories. This is a generalization of the previous two. And by myself and Shlomo Eshel, my student, last year for any NIP formula. And there's still an open question there, namely, so can the defining formula be chosen to have NIP as well? I know the answer is yes, if I'm assuming that there are Skolen functions in the language, but otherwise I don't know. So yeah, this would be, I think this is an interesting question. Okay. Now I'm continuing with honest definitions. So suppose phi of xy is a formula, A is some set of x tuples, and B is some parameter, some y tuple. Say that some formula psi is an honest definition of the type of B over A if for every A0 subset of A, finite, there is some C in A to the Z such that the following implication holds. So phi of A0B is contained in psi of AC, which is contained in phi of AB. Okay, so a definition would be equality in all sides with A0 replaced with A. So, but honest definition only promises this for finite sets A0. Okay, so for finite sets A0, so you get one direction for the finite set and the other direction all the time. That's honest definitions. Okay, and then there's an explanation again. So if A is in A, if psi of AC holds, then phi of AB holds, always. But for A in A0, we also promise the other direction. Okay. So Chernikov and Simon proved something stronger than UDTFS, namely that if T is NIP, then for every phi, there is some formula psi, which depends only on the original formula phi. And this formula psi will be an honest definition for any phi op type. So they proved uniformity. In other words, they proved uniformity of honest definitions. Okay, and here's the theorem I want to present, that namely that uniform honest definitions exist for NIP formulas without assuming that the full theory is NIP. So more precisely, if phi of xy is NIP, then there is a formula psi of xz which serves as an honest definition. And again, I'm repeating the definition because for people who didn't see it, it takes a while to get used to it. So again, it says for any B, y tuple, and any A, set of x tuples, and any finite A0 subset of A, there is some C in A to the Z, such that this inclusion happens.
Excuse me, may I ask you something right now?
Yes, of course.
So I have a silly question. So why you are not, no, it's like, why you are not choosing the obvious honest definition like phi? I mean, why do you?
Oh, because the issue is I want C to be from A. B is from somewhere.
Ah, I see. Okay, but what? So what does it have to do with type? Because there was like a dependence on type B over A, right?
No, there was never a dependent on a type.
Oh,
Okay. I mean, before maybe
yes.
Before it was here. So I'm looking just at B. So saying the type of B is the same as looking at B. B, right? B causes the type. It's the same as saying for any B.
Okay.
Okay.
Thanks.
Yeah, sure. Yeah, please feel free to ask questions even without, not even in the chat. It's okay. So this I explained. So when I take A finite, okay, if I take A to be finite, then I get exactly UDTFS because then I get equality here. So UDTFS just says I really have a definition, and then I can take A0 to be equal to A, and then actually get equality. So again, this is a stronger theorem than just UDTFS. Okay, so for the proof, I will need to introduce the notion of K-compressible local types. Okay, so let pi be some pi of x be some partial type, and this set S phi pi of A is the set of phi types which is consistent with pi. Okay, so this is a closed set, a closed subset of the set of all phi types.
So pi is over A or what?
No, not necessarily. But I am assuming that it is. I'm allowing myself to assume that it's small, namely number of formulas there is small. No, but pi doesn't. It doesn't have to be over A.
S pi phi is complete types over phi types over A.
Yeah, but this is a subset of phi types over A.
Complete phi types over A.
Complete phi types over A. Yes, which are consistent with this pi, which doesn't have to be itself over A. Okay, so suppose that phi is a formula, and pi again is a partial type. A is some subset of C to the Y, now of Y tuples, and K is some number. So say that P, so P again is a phi type, is K compressible modulo. There's a missing pi here. There's supposed to be a pi here. Sorry. Is K compressible modulo pi? I mean, okay, I should say without the modulo pi, there is no pi here, but with the modulo pi, there should be a pi. So sorry. If for any finite A0, there is some A1 of size at most K, such that P restricted to A1 implies P restricted to A0. And in the modulo pi definition, I also add pi on the left side. So I only ask for the implication to hold modulo pi. So the notation, this notation is the space, a subset of the space of types of all K compressible types. Okay. So similarly, we can define K isolated modulo pi if we replace A0 by A, namely, instead of asking that P restricted to A1 implies P restricted to A0, I ask that P restricted to A1 implies P. Okay, so it's isolated, really. This is the notion that you would expect. Okay, so when A is finite, K compressible is the same as K isolated. Okay, because then I can take A0 to be A. In the theory, let's look at this theory of the natural numbers with the order. Okay. Then, if we look at the type of omega, so omega, I'm thinking of omega as infinity. Okay. So the type of omega over the natural numbers is one compressible, because to say that X is bigger than some finite set, doesn't matter which size, it's enough to say that X is bigger than the last one in that set. So that's only one. I only need one instance. But if I look at the type of equality of omega over the natural numbers, then it's not K compressible for any K. I cannot say by stating finitely many equalities that are not equal to the next guy. Okay. And actually, we can prove that for stable formulas, K compressibility is equivalent to K isolation. Namely, if a type is K compressible, then it is already K isolated. Okay, how is this connected to UDTFS? Let me explain. So in the work with Eschel, we proved UDTFS via the following theorem. So the theorem was, you have formula phi, which is NIP. Then there are some natural numbers, K and N, which depend only on the VC dimension of phi, such that for every finite set A and every phi type P of Y, so here A is finite, okay? There are N types such that each one of them is K isolated. So these are types over A, and each one of them is K isolated. A could be finite, but we don't have any bound on the size. But we do have the K isolation is for this K that we chose above. So that's the first bullet. The second bullet is that P is the rounded average of the types Q0 up to Qn minus 1, which means that for any C in A and every epsilon could be 0 or 1, the set of i's for which phi of Cy agrees, so phi of Cy is in P, if and only if phi of Cy is in Qi, namely the set of i's for which the truth value of the formula belonging to P agrees with the truth value of the formula belonging to Qi, is bigger than half of the n's. So,
Itay,
yes.
What's the role of epsilon in
Epsilon
the
is 0 or 1 here. Well, yeah, I forgot. Yeah, good point.
Okay.
There should be epsilon here and here. Yeah, sorry, that's a mistake. Yes, is that okay now?
Yes.
Yes, okay, sorry, yes, thank you. Yeah, so they agree on the belonging. The majority agrees. Okay, now, okay, so that's, I'm going to repeat, I'm going to go back to this, but sorry. I'm going to go back to how I'm using this, but for now, just let me say a little bit about the proof. So it combined two results from machine learning theory. One is by Moran and Yehudayev from 2016, which proved the existence of sample compression schemes for VC classes. And the second one was by Chen Cheng Tang, which found a bound for the recursive teaching dimension, which depends only on the VC dimension. So I'm not going to go into the details of this at all. I'm not going to define any of these things because we don't need it. But I'm just going to say the other ingredients fit in the proof. So the proof of the first part, Moran-Yehudayev part, this gives the rounded average, and the CCT, namely the second part, gives the existence of the K isolating types. Of course, so remember the statement was that every phi type is a rounded average of K isolated types. So the second part gave the K isolated types, and the first part gave the rounded average. Okay. So we wanted to generalize this to not necessarily finite sets A. So far we had finite sets, and now we want infinite sets. So the first part of the proof would be to reproduce this part, namely to generalize the CCT result, which gives the existence of K isolated types. So again, CCT gives the existence of K isolated types for finite types, but now we want it for infinite types. Okay, so here's the statement. Suppose that phi is NIP, then there is K depending only on the VC dimension of phi, such that for any partial type pi, and for any A subsets, any A of set of Y tuples, the set of K compressible types is not empty. the set of K compressible types consistent with pi is not empty. So this shows that star compressible types are dense. So star compressible means K compressible for some K. Okay, so this means this set of this is the set of K of types which are K compressible for some K is a dense subset of the space of types consistent with pi. Okay, now this was namely the second ingredient, and now we want to get the rounded average part. Okay, so here's the theorem. Let D be some number and alpha be some real number. We give a slightly generalization of the rounded average, like with there is this extra ingredient alpha. Before alpha could be just 1/2, but we give a little bit more. So alpha is some real number in this interval. Then there are n and k, which depend only on these two numbers, d and alpha, such that the following holds. If phi is such that the VC dimension of phi is at most d, then for any a and any partial type pi, any phi op type, which again is consistent with pi, is the alpha rounded average of n types which are K compressible. Namely, here's the explanation, there are K0 up to Kn-1. These are all K compressible types, such that, yeah, there's a, I made a mistake here. There should be also epsilon and also here. And again, for all epsilon less than 2, sorry about that. Yeah, so there are Q0 up to Qn-1. These are K compressible types, such as for any C and for all epsilon less than 2, we have that the set of i's in N for which phi of Cy to the epsilon is in P, if and only phi of Cy to the epsilon is in Qi, is bigger than alpha times N. So it's the same statement as before, but here alpha, it could be any number between 1/2 and 1, and there it was just 1/2. But the big change is that we don't necessarily assume that A is finite here. I'm just saying any A. That's a change here. Okay, are there any questions so far?
I have one.
Yes.
So is it important to look at types pi? Why can one not work with formulas instead of a type pi?
Why is it what? Important to look at what?
At partial types pi and not just at formulas.
Oh no, I mean this is better, right?
Yeah, it's better, but is it important that is it much better or?
No, it's the same. I mean, it would be the same difficulty.
It would be the same, okay? Because if you talk about density, then it should be
for density. It's enough to look at formulas. Yes.
Okay.
Yeah. Yes. So as far as I know, this statement was not known even for stable theories, for stable formulas. Sorry. Correct me if I'm wrong. If anybody knows differently. So for stable formulas, if I was stable, this statement would say that every phi type is a rounded average of n k isolated types. Not k, because again, when phi is stable, then k isolated is k compressible is the same as k isolated. So yeah, again, I don't know if this was known. I think it wasn't. Okay. So how do we get from this to local uniform honest definitions? So I want to deduce the theorem. So let me first remind you what the theorem was. The theorem was that you have some phi, which is nip. Then there is some formula psi, such that for any b, y tuple, and any a set of x tuples, and every a0, there is some c in a to the z, such that you have this inclusion. Okay. So I want to explain how to find this psi using rounded average. So let's apply the previous theorem with alpha equals 1/2. So let me give here the idea of the proof. So suppose we have n equals 3, mainly the number of types needed for the rounded average is 3. So suppose that the type of I over B, the type of B over A is the rounded average of 3 types, namely these 3, okay? Q1, Q2, Q3. Now I'm given some A0 which is finite, and then by the fact that these are K-compressible, there are some BIs which are all of size at most K, such that the restriction of Qi to Bi already implies the restriction of Qi to A0. A0 could be any size, but the Bis are of size at most K. Okay, then take A0 from A0. Suppose that phi of A0B holds. Then by the fact that this is the rounded average, for at least 2 of the Qis, phi of A0y is in Qi. Okay, and then for at least 2 of the Qis, Qi restricted to Bi implies phi of A0y, because again, this is what it says here. Okay, so this says that if phi of A0 is in B, then for at least 2 of the Qis, you have this implication. Okay, on the other hand, if A is any guy in A, not necessarily in A0, and at least 2 of the Qis satisfy that Qi restricted to Bi implies this instance, then I know, because the type of B over A was the rounded average, I know that phi of AB holds. Okay, so this gives me this set of inclusions. And I can call, since there's only finitely many possibilities for this implication, for how what does Qi restricted to Bi look like, because it's bounded by K, I can code this statement here by finitely many formulas, and then code finitely many formulas as one formula, because I'm assuming A is at least size of A is at least 2. Yeah, maybe I forgot to say that I'm assuming I should have said here that A has size at least 2. So let me just write it here. So yeah, I'm supposed to assume that A is at least 2. Otherwise, you won't get this. Okay, so this is how you get honest definitions from the previous theorem. Okay, now let me move to something a bit different, namely hypes. So here's the definition. So I'm fixing some formula phi and some K. K hype in phi op over A is a collection gamma of instances of phi and the negation of phi, such that over A, such that sorry, it is K consistent. Namely, if I take a subset of size at most K, then it is consistent. And the second bullet is that for any A, either phi of AY is in gamma or the negation, but not both. Okay, so it's kind of complete.
Right, so the instance of phi op, not phi.
Again, what?
The instances of phi op.
Yeah, these are instances of phi op, yes. Did I say instances of phi? Yeah, I meant, yeah, here it should be phi op. You're right, absolutely. Oh, what happened? Yeah, so op. Okay. Okay, so here's the theorem. The theorem is the same statement as before, but now I'm assuming that the same theorem as before, but for hypes. Namely, let again D be some number and alpha be some number between 1/2 and 1. Then there exists some n, there exists n and k, which depend only on D and alpha, such that if phi is such that the VC dimension of phi is at most D, then for any A and any K hype gamma over A, is any K hype gamma is the alpha rounded average of n types and K compressible types. Okay, so same statement as before, but we don't require that these are types. We don't require these are really consistent, only that these are K consistent for some K, which is only depending on the VC dimension of the formula. Okay, and then from this we can deduce that K hypes have uniform honest definitions as before. Okay, now why is this useful? Because now we can talk about pseudofinite types. Okay, so I'm going to define what is a pseudofinite type. So yeah, it's not a difficult definition, but I'm going to be precise. So let L prime be L when I add two unary predicates. And I'm assuming here that phi is some formula, M is a model, D some subset of X tuples, and P is some type, some phi op type over D. Then for epsilon less than 2, again, epsilon is 0 or 1, let D to the epsilon be the set of the epsilon instances of P. Then we say that P is pseudofinite if for every L prime sentence phi, if the triple satisfy phi, then there is some L prime structure N such that N satisfies phi, and the interpretations of the predicates in N are finite. So this is the same. This is an example. Just if you didn't internalize this definition, so here's an example. If M is itself an ultra product of finite structures, and AI is a set of X tuples, and we take A to be the ultra product of the AIs, then take P. We can take P so that D0, so the false instances of phi, let's say, is this A. Okay, so in other words, the set of positive instances is internal, if you want, and then the set of negative instances is internal as well. So that's the example you should keep in mind. Okay. So here's a corollary of the Hype's theorem. Namely, we get uniform definability of pseudofinite types. So we added the P to the UDTFS. Suppose that phi is NIP. Then there is some formula psi such that whenever M is whenever M is a model of T and D is a subset of M to the X of size at least 2, and P is some pseudofinite type over D, then P is definable by an instance of psi over D to the Z. So if you think about it, this doesn't follow immediately. You would think that this follows immediately from UDTFS, but if you try to do the proof, you will get stuck because you can't get consistency of the type. That would be the issue. You can only get K consistency when you go to the finite part. And moreover, if T has column functions, we can choose psi to be NIP. Okay, any questions? Okay, so again, this might seem like it would just follow from UDTFS, but actually it doesn't. I thought it did, actually. Okay, now let me move to the global part of the talk. So I'm going to start with compressible types. So far I talked about K-compressible types. Now I'm looking at complete types as opposed to local types. And I'm saying that a type is compressible if for any formula phi of xy, there is some formula psi such that for any finite set A0, there is some C in A to the Z, such that the formula psi of xc is in P, and the instance psi of xc implies P restricted to phi. Okay, so before we had K compressibility, which means we took K instances. And now I'm saying it's not exactly the same. We're taking some other formula in the type, but this is a complete type. We're taking some other formula in the type, but this formula, psi, is in charge of compressing the phi part of P. That's how we think about it. So if you think about it in DLO, like meaning the rational numbers with the order, then every type is compressible. So for example, the type of pi over the rational numbers is compressible because we need to compress, we need to say when x is, let's say, between y and z, so it's enough to take, for the finite set, it's enough to take the minimal guy, which is above x, and the maximal guy, which is below x, and this will decide the cut. Okay, and in fact, the theory is distal. A theory is distal if and only if every type is compressible, and DLO is an example of a distal theory. But I won't need I don't need to get into distality.
Itay, there's a question in the talk. Is there a connection between psi and phi?
Well, I mean, it's uniform. Psi depends only on phi. Does that answer the question? I mean, a priori, no. There's no question except that it's uniform. That's the definition. Okay. Yeah. So here's the theorem that if T is countable NIP, then for any set A, compressible types are dense. Yes.
I guess maybe the question was, maybe, I don't know, if you could take psi to be in the phi type.
Again, what?
Is there any connection between psi and phi? So say, can you take psi to be in the phi type?
No, not necessarily, no. I mean, psi could use formulas which are not phi. I mean,
it's not
yeah.
local.
What?
It's not local in any.
No, not the definition. No, it's not local. No. It's only a definition. Okay, it's not a statement. So this definition, I want to make it as big as possible, right? And why would I want to restrict phi necessarily? But then in the theorem, when you prove that such a type exists, maybe the construction gives you some more information about how this psi looks like.
But Martin also.
I didn't hear you.
Oh.
But yeah, maybe I didn't hear you. But okay. So again, the theorem is if T is countable and then IP, then for any set A, the compressible types are dense. Namely, if we start with some consistent formula over A, then there is a compressible type P which extends this formula. And how to prove this? This is very easy from the previous density statement. You just go over all the formulas and you build it one by one. You start with let's say we start with phi, and then you know there is a K compressible type extending phi, and then you keep this type and you call it pi. Okay, yeah. Actually, Martin, now that I think about it, no, you need pi. So now you fix this. You fix this. It's not enough to look at formulas. You have to look at types. So now you look at this compressible types. You already partial compressible types you constructed. You call it pi, and now you used again the local compressibility density, the local density result to go to the next formula and so on. But you need countability for that. Obviously, you need countability for this construction to work. And it's not true. The statement is the theorem is not true if T is not countable. Okay. And there is a counterexample, and even for stable theories, it's not true. Okay. And now, now I mentioned stable theories. So I want to mention a couple of results that imply that under stability, compressible is the same as L isolation. So let me define what it means, L isolated. So a type, now again, a complete type is L isolated if for any formula phi of xy, there is some formula psi of xz and some c such that psi of xc is in P and psi of xc implies the full phi type. So as opposed to before, when we only wanted it to imply the phi type restricted to a finite set, here I want to imply the full phi type. Right, here's a fact. So if T is countable and stable, then L isolated types are dense. And you can, so this is very similar to what we saw before, namely every consistent formula over any set extends to an L isolated type. The proof of this is not difficult. It uses the 2 rank. So it's classical. And here's a connection with stability. Namely, the first bullet is that if T is stable, then L isolation is the same as compressibility. Namely, a type is compressible if and only if it's L-isolated. One direction is clear. If it's L-isolated, then it is compressible. L-isolation is way stronger, but this is the other direction. Moreover, the same is true for stable types. You don't need the full theory to be stable. It's enough to look at stable types. And the second part is that if P is a global, the second part is in any theory. If P is a global type which is generically stable over A, there's a definition of Anand and Predrag of a general generically stable type. So the statement is that if you have a global type which is generically stable over A, and the restriction to A is compressible, then actually this restriction is L-isolated. Okay. Now I want to talk about compressibility as an isolation notion. So we work in a countable NIP theory, complete also. I want to say that a set B is compressible over A if for every tuple B from B, B could be, B is, little b is any finite or even infinite tuple if you want. For any tuple B from B, the type of B over A is compressible. Okay. So that's a notion of compressibility. This is like, if you remember the notion of atomic model over something, this is the analog thing. So a set is atomic over A if every tuple from that set, the type of it over the set is isolated. So again, we want to look at compressibility as an isolation notion. So it's very similar. And as in the atomic case, as in the totally transcendental case, we have constructible models, very constructible sets and models. So B is compressibly constructible over A if there is some enumeration I less than alpha, such that this is enumeration of B, such that for any I less than alpha, the type of the I guy, AI, is compressible. The type of AI over the previous guys is compressible over A. Okay. And proposition is that given any set A, there is a model M, which is compressibly constructible over A of cardinality A plus Aleph 0. And the proof of this just uses density. Okay, just use density. You want to satisfy the Tarski-Voss condition. So using density, you can do it. Okay. There is a well-known analogous statement for stable theories. Namely, you can build L-constructible or L-isolated, I don't know how to say it, L-constructibly, I wouldn't say it, L-isolated constructible models. And these are called L-atomic models. Actually, yeah, I wrote it down, so I should have just read what I wrote. And namely that you get that the type of A over A, you get something stronger. You get the type of any tuple from the model, the type of it is L-atomic. Namely, it's L-isolated. L-atomic and L-atomic is the same as L-isolated here. Okay, so we want something similar here. We can do this constructible thing. We can construct models, but what we don't necessarily see is that the model we get is atomic in the right sense. We don't know that it's compressible. Do you see the issue? So we get that it's constructible, but we don't know that it's actually compressible. So okay, so let's talk a little bit about these models. So the theorem is that if B is compressibly constructible over A, then it is actually compressible over A. Okay, we actually get this. We get what we wanted. We get that if we can construct something compressibly, then it's actually, the set itself is compressible. Let me give some corollaries of this. So here's one corollary. If A is such that the induced structure on it is stable, then there exists a model M containing A, which is L-atomic. Okay, Namely, every tuple from M, the type of every tuple from M over A is L isolated. And
are you assuming NIP or anything?
I'm
here?
assuming NIP. Yes, yes, yes. I'm assuming the theory is NIP. Yes. Okay. Even I'm assuming NIP even uncountable even to construct this model. Okay. And second part, if A is such that any model containing A has a definable p-order with an infinite chain, then there are arbitrarily large compressible models over A. Essentially because once we have a p-order with an infinite chain, we can always find a compressible type which is not realized. So we can increase the model, and then we can use the construction to build a compressible model. And the last corollary, I think, is that if M is a model, you have some definable set which supports a definable p-order with infinite chains, then for every cardinal lambda, we can find some elementary extension such that the D part of this elementary extension is of size at least lambda. But if I take some guy from N and whose type over the model M is generically stable, then A is already in M. So I don't realize any new generically stable types. In particular, if I have some stable definable set around, then it remains the same. So I can increase the older part while fixing the stable parts. So here's an example that actually the example requires the theorem, and namely in ACVF, if we have some subset of MEQ such that the residue field K of M is actually ACLEQ of A intersected K, so it doesn't the residue field in M is the same as the one in A, then M is actually compressible over A. And it's also true that the converse is true, namely if in order for it to be compressible, you need this intersection to hold, but this only if A intersected K is infinite. Otherwise, if A is finite, for example, then every model is compressible over it, so it will require A to be infinite. Okay, so this is an example of compressible models. Namely, we don't change the residue field.
There's a question from the chat. What is supporting?
Yeah, there's a fancy word for saying there is a definable p-order contained in D. That's okay. Namely, the domain of the order is D. That's sorry. So let me give you a bit on the proof because it's not so trivial. So the difficulty, what is the difficulty? We want to show that I'm explaining the proof of how to get from a constructible thing to a atomic thing. Okay, so suppose we have this construction, I less than alpha, such that for any guy I, the type of AI over the previous guys is compressible. How do we know that the type of AI itself is compressible over A? So that's the issue. So in the L isolated case, this is easy because the isolating formula, so we know that, that there is some isolating formula of the type of AI over the previous guys, and this has some fixed parameters from the previous guys. So these parameters are themselves L isolated. Okay, so but here, so we can use some trickery with formulas to get what we want. But here, the parameters change. If we change now we want to show it's compressible, and we have some finite. We change the finite subsets, and the parameters may change, and then we have no control on the. So on the we can't continue with this easy argument. So what we want is we want a sensitivity lemma, namely that if A contained in B contained in C, and C is compressible over B, B is compressible over A, then C is compressible over A. And we can prove this lemma using the following proposition. This is a characterization of compressible types. So the type of A over A is compressible if and only for any global type Q, which is finitely satisfiable in A, and any Morley sequence of that Q, we have the implication that Q restricted to A, and the Morley sequence implies Q restricted to AA. So the Morley sequence realizes Q over A, not over AA, but but we have this implication that once Q restricted to AI implies Q restricted to AA. So I'm saying this is the definition. So P is compressible up to B if it is compressible when we add constants for B. Okay, and the lemma is that if you have a type over B which is compressible and A some subset, then the restriction of P to A is actually compressible up to B. Namely, it is compressible, the restriction is compressible, but we need these extra parameters from B. So it's compressible in this language where we add constants for B. So I wanted to explain the proof of this, but I don't have time, so I'm just saying that the proof uses Pierre's type decomposition theorem. It's an application of the type decomposition theorem that he proved a while ago. And here's if you're able to read it, then okay. But otherwise, I want to thank you for your time.
Thank you, Itay.